Okay, so in the last class, we had started talking about when you have a continuous time signal GA of t and you sample it with some rate t to get Gn, what is the relationship between the Fourier transform of this GA of t, which is called GA of j omega, and Gn, which is G of e to the j omega. And the way we derive that relationship is we said the way to get to Gn is in two steps. You first go from GA of t to this first transition block, which essentially does that impulse sampling to get to GP of t. Okay? And then you have the second transition block, which is you go from GP of t to the samples. So these are sort of the mathematical blocks. You don't have them in reality. And we already knew the relationship between the Fourier transform of GA of t and GP of t. And then we derived the relationship between GP and the Fourier transform of our discrete time signal. And so using these three steps, we know the relationship between these two, we know the relationship between these two. We derived the final relationship between the continuous time and the discrete time Fourier transform. The relationship that came up was this: G e to the j omega equals to 1 over t, summation k from minus infinity to infinity, Ga of j little omega minus 2 pi k over t. And the way to interpret this relationship is that what happens if you are given a Fourier transform is you first scale the axis of that Fourier transform, the continuous time Fourier transform, by a factor of capital T. Right? That's due to this omega over t relationship. And then you get multiple copies of that scaled Fourier transform at locations plus 2 pi, minus 2 pi, and there is a final scaling of the amplitude by 1 over t. Okay. So in particular, what we saw was that the frequency, the pi frequency in discrete time actually corresponds to the pi by t frequency in continuous time. Okay. So that's sort of where the folding happens, right? Pi by t is the location where folding of your frequencies happen, and the highest frequency in discrete time is always pi, which is in relation to continuous time, it's pi by t. So what is the physical significance of this relationship? Here is an example. You are asked that you are given a signal, continuous time signal. So say GA of t is a voice signal. Okay. And then you pass it through an anti-aliasing filter. With cutoff of 44 kilohertz, with cutoff of 4 kilohertz. And after we pass it through the anti-aliasing filter, we are told we sample it with sampling frequency f of t equal to 12 kilohertz. Okay. So what do these continuous time frequencies mean then in the discrete time world? So let's say you have this GA of t. You first pass it through an ideal anti-aliasing filter, HA of j omega, which has a cutoff of 8000 pi. radians per second, and then we sample it with the time period t equal to 1 over 12,000 to get g of n. What can we say about the Fourier transform of Gn? Okay. So once we pass Ga of t is passed through an anti-aliasing filter with omega c equal to 8,000 pi. So let's call this G tilde of A of t. So what does it mean that we have passed it through an anti-aliasing filter of cutoff frequency 8,000 pi? This means that the Fourier transform of G tilde A, which is G tilde, let's say G of G omega, it cannot have any frequency above 8,000 pi. We have low pass filter it cannot have any frequency above 8,000 pi. So this means that this is equal to 0 for all omega greater than or equal to 8,000 pi. Right? That's the meaning of low pass filtering. Well, what would it mean in terms of the discrete time frequencies? So what can we say about Ge of j omega? Okay. So if you remember this relationship, the mathematical relationship is given here, but what it effectively means is if you want to focus on the frequencies in the minus pi to pi range, you are going to get a copy of G tilde A of j omega. First of all, it will be scaled by capital T. So let's say that G tilde A of j omega, it could be any shape, but I'm going to just use our commonly used shape A. So this is 8,000 pi and minus 8,000 pi. Okay. So according to the relationship, if you want to compute Ge of j omega, first of all, you scale the axis by capital T. So this is omega axis. I want to take it to little omega axis. I first scale it by capital T. So what will 8,000 pi become after I scale it? What will be these endpoints after I do the scaling of the frequency axis? This will be 8,000 pi over 12,000, which is 2 pi by 3. And similarly, this will be minus 2 pi by 3. So that is the first aspect of what you do if you are converting from continuous time frequencies to discrete time. You take your Fourier transform and you scale the axis by t, capital T. Now what's the second step? The second step is that there is a periodic repetition of this scaled transform. So you now take it, place it at 0, 2 pi, minus 2 pi, and so forth. Okay. So the next step is you actually get the same thing. You will have it at 0. So you have this 2 pi by 3 minus 2 pi by 3. You have another copy at 2 pi. Now 2 pi by 3, you can always make sure after you scale this, if the endpoints are within pi and minus pi, you won't have any overlap. So you have this copy here. This point will be 2 pi minus 2 pi by 3. Okay. Similarly, you will have another copy at minus 2 pi, and you will have periodic repetitions. And minus pi is somewhere here, pi is somewhere here. And the final step is, so this is the second step. And the final thing that you need to account for is this 1 over t factor. Okay? So the first step basically accounted for the scaling. The second step that we did accounted for this periodic repetition and the summation. And the third one is you have a scaling of the amplitude. So what you get is instead of A, you will have A over T. All the amplitudes will be scaled by 1 over T. Okay. We could have done it in one step, but I wanted to do it more in a more methodical fashion. So the end result is that since your signal was the one that you sampled was band limited to 8,000 pi or 4 kilohertz, okay, after you sample it, your discrete time signal now is actually band limited to, it is band limited to 2 pi by 3 radians per sample. So this discrete time signal is also band limited to 2 pi by 3 radians. Now, just another view of this translation. Let's say someone asked you that what is the amount of 2 kilohertz frequency present in G of A j omega, or equivalently G A of t. Okay. So someone asks you, tell me something about the 2 kilohertz frequency. Since you have low pass filtered it up to 4 kilohertz, the 2 kilohertz frequency has still survived. Right? And since you have sampled it at such that you satisfy the Nyquist criterion, the 2 kilohertz frequency, you know, hasn't been corrupted by any aliasing. So all you have to do is basically look at what is the corresponding location of 2 kilohertz in discrete time. So how do you find? So instead of looking at GA of j omega, what you can do is look at GE of j little omega with little omega that corresponds to 2 kilohertz. So what is the, how do you find the little omega that corresponds to 2 kilohertz? Using this relationship that the discrete time frequencies are simply given by continuous time frequencies multiplied by t. Okay. So if someone says, tell me something about 2 kilohertz continuous time frequency, that is equivalent to little omega equal to 2. So we now have to do it in radians. So that's 4,000 pi times 1 over 12,000. That is pi by 3. Okay. So if you want to tell something about the 2 kilohertz frequency, what you do is you look at e to the j pi by 3, and that gives you an information about the 2 kilohertz frequency. There is also the scaling of t factor that you have to account for. But in general, the 2 kilohertz frequency in discrete time is equivalent to pi by 3. Okay? So as long as you know this relationship, that the only way that the two frequencies are related to each other is through multiplication, I can tell you anything about continuous frequencies and you know what the corresponding frequency I'm talking about in discrete time. So this explains the relationship if you are sampling a discrete time, continuous time signal to get a discrete time signal. Now the other question is, what is the relationship? So now we want to talk about between the DTFT of some samples, and the reconstructed continuous time signal. Okay? So the general representation is I can give you a sequence, and I don't have to tell you where the sequence came from. I can give you a sequence, and you can do its discrete to continuous conversion to get something called, let's call it G1 hat T. Now to do discrete to continuous conversion, I need to supply your reconstruction system some sampling time. So let's say I supply T1. Let's say I took the sequence and I supplied T2 to get G2 hat T. What is the relationship between the Fourier transform of my samples and the reconstructed continuous time signal? Okay. We don't care where Gn came from. We just want to look at, once we do this operation, what do we get? So to understand that relationship, we want to go back to how the reconstruction formula works. Okay. So I just want to remind you the way we derived the reconstruction with time t to get G hat of A of t is the following. We said it's given by an interpolation formula that G hat A of t equals to summation n from minus infinity to infinity G of n HR of t minus nt. Okay. Mathematically, what we had done was that we had broken this block into two pieces. We had said that you first convert this Gn into impulses with period t to get Gp of t, and then you pass it through what we called a reconstruction filter. So we had a reconstruction filter HR j omega, which has an impulse response HR of t. And if you do this, then we had derived that this is the expression of your output. This is what the output looks like. This relationship is always true, regardless of whether you are doing sync interpolation or not. What does sync interpolation mean? That HR of j omega is a perfect ideal low pass filter with height capital T. Right? But even if this is not a sync interpolator, if this is not an ideal low pass filter, this boxed equation always holds. So let's compute the Fourier transform of this output. So I want to compute the Fourier transform of G hat of A of t. I just compute the Fourier transform of this summation, and from minus infinity to infinity Gn HR of t minus nt. Okay. I call this G hat A of j omega. Now we have done this trick many times. This is Fourier transform is linear. We take it inside. And once we take it inside, we are computing continuous time Fourier transform. So from the perspective of continuous time Fourier transform, this Gn is just a scalar constant. So I can actually just write it outside, and I get Fourier transform of HR t minus nt. Okay. Now what is Fourier transform of HR of t? We call that HR j omega. So what is this thing? This is Fourier transform of time shifted HR of t. So Since Fourier transform of HRT is HRJ omega, Fourier transform of HRT minus NT is simply going to be HRJ omega times e to the minus j omega NT. Just a phase term is added. So I just plug that in. This means I get G hat A of j omega equals to summation n from minus infinity to infinity G of n HR j omega e to the minus j n omega t. Now this HR j omega is not a function of n, so I can take it outside the summation. So I get summation HR j omega times summation n from minus infinity to infinity Gn e to the minus j omega Tn. Okay. This is my G hat A of j omega, which is what I get if I use my sequence to construct a continuous time signal. So you record my voice and that you are given a sequence of samples. If you convert it into something that you can hear continuous time, this is the relationship you get. Our final goal is we want to relate this G hat of A j omega to G of e to the j omega. Okay, this is our final goal. So to do that, let's call this equation star. And let's say, what is G e of j omega? Well, that is simply the Fourier transform formula G of n e to the minus j omega n. So let's compare this thing that is inside these brackets to this formula. What do we see? These are exactly the same formula, except that instead of little omega, you have capital omega t. So this is nothing but G e of j omega with little omega replaced by capital omega t. Okay. Remember how when we were going from continuous time to discrete time, we had that you get almost the same expression with capital omega replaced by little omega over t. This is just a reverse version of that. You get little omega equal to capital omega over t. So if you want to write down then the formal relationship, what you get is when you take a sequence and you convert it into a continuous time signal, what this means in frequencies is that the Fourier transform of G A hat j omega becomes equal to HR j omega times G of e to the j capital omega t. This is what the relationship becomes. Okay, and this is always true regardless of HR j omega. It doesn't matter whether HR j omega is a sinc interpolation filter or not. Okay, this is always true. What is the meaning of this relationship? Let's try to break it down into two pieces. Let's call this 1 and let's call this 2. Okay. What this is saying is that first of all, so you are given Gn. The Gn has some Fourier transform. So let's say this is Gn's Fourier transform. This is, assume this is minus pi and this is pi. And this is some value b. Okay. Where this Fourier transform came from, we don't care. You could have just synthesized this thing. Right? You can, for example, use a digital system to synthesize artificial sequences. Right? We don't care where it came from, but it has the Fourier transform, which has to be, of course, periodic, and it keeps on going minus 2 pi, and so forth. So the first step is saying what? This is little omega axis. The first step is saying you replace little omega axis by capital omega t. Now at the end of the day, you want something which is a function of only capital omega. So what do you do then? You scale to get from little omega equal to capital omega t to capital omega. What should we do? When we were going from continuous time to discrete time, we were multiplying frequency axis by capital T. This is saying we divided by capital T. So this is what we get. Of course, when you divide your axis by capital T, the shape of the axis is going to just either stretch it or compress it. The shape of the Fourier transform doesn't change, right, when you change your axis. But what happens? This pi, where does it end up? This pi becomes pi by t. This minus pi becomes minus pi by t. 2 pi becomes 2 pi by t, minus 2 pi becomes minus 2 pi by t. Okay? No change to the amplitude. This is the first step. What is the second step saying? The second step is saying that you now pass it through a filter whose Fourier transform is given by HRJ omega. So this HRJ omega could be anything. You are going to multiply this with HRJ omega. Okay? Let's say the HRJ omega was actually an ideal low pass filter. It could be anything, but let's say that it was actually this, T for omega less than or equal to pi by T and 0 otherwise. What happens in that case? You low pass filter between minus pi by T to pi by T with height of T. What do you get? All the other copies, all the other regions get zeroed out, and you only get from minus pi by T to pi by T with a height of BT. Okay? So that's the relationship that you get if you were going from discrete time to continuous time. In particular, the frequency relationship still holds if you have little omega equal to capital omega t, which means that capital omega is little omega over t. So if I give you a frequency of, let's say, 2 pi by 3 in continuous time, when you do the conversion in continuous time, that will become 2 pi over 3t. Okay? It's almost the reverse of what we saw when we were going from continuous to discrete, except that you have this reconstruction filter that you have to account for. Okay? And if this Gn, if you go back to our previous cases, if this Gn was really obtained from a continuous time signal, then actually in that case, this new signal G hat of A of t will be exactly the same as what you started with. Now, in the case of an ideal reconstruction filter, I can also actually give you a sort of cheat formula, which is that if the reconstruction filter is ideal, you have to do these steps if it is not ideal. But if HR of J omega is an ideal reconstruction filter, which always means the magnitude of T for omega less than or equal to pi by T and 0 otherwise, or the equivalent way of saying is if you are doing sinc interpolation, if that is the case, if you notice, then what is happening? You are filtering from minus pi by T to pi by T, but before scaling that was minus pi to pi. Now, discrete time Fourier transform is periodic. So what that is saying is if you have an ideal reconstruction filter, okay, then all you have to do to obtain GA hat of J omega, we simply take the principal period of G of E to the J omega, and by principal period I mean that omega less than or equal to pi, okay, and then scale that principal period in frequency by 1 over t, so you divide by t, capital T, and in amplitude by capital T. Okay, so if I gave you, let's say, Gn, which had a Fourier transform of like this, minus pi to pi, and of course it's going to repeat itself, 2 pi minus 2 pi. And if I say that the reconstruction filter is ideal, you are doing sinc interpolation, then you actually don't have to do all the steps. All you have to do is you just focus on the principal period and your output. So let's say the height of this was b. You just scale the frequency axis of the principal period to get pi by t minus pi by t, and the height will be bt. Okay. But if you don't have an ideal reconstruction filter, then you have to do the steps that we had talked about. So this is G of E to the J omega. Then you have to scale the whole Fourier transform and then pass it through the filter. So let's take a simple example of a pure sinusoid. So let's say you are given Gn equal to cosine of pi by 3n. You are given Gn equal to cosine of pi by 3n, and what's the Fourier transform of that? You get an impulse at pi by 3 of height of area pi, an impulse at minus pi by 3, this is minus pi, this is pi, and then you get it, you get repeated copies of that at 2 pi, minus 2 pi, and so forth, right? And I tell you that you have Gn and you are going to pass it through this discrete to continuous filter with period t, and you get Ga of t. And I want you to tell me what is Ga of t, or what's the Fourier transform of Ga of t equivalently. Well, and I say that the reconstruction is ideal, which means that you have ideal reconstruction filter. In that case, all you have to do is scale the axis, just focus on the principal axis. So the principal axis becomes minus pi by t, okay. Now this location becomes pi over 3t, this location becomes minus pi over 3t, and you also have to scale the amplitude. So you the area, this is pi, both of them are pi. Okay. Now remember one of the questions in the first homework, that if you have delta, if you scale your delta, you get an additional factor. So let's say if you scale delta x of a is equal to 1 over a delta of x. So what happens is, because of actually, just in the case of impulses, when I change the frequency axis, I get a 1 over t due to that, and then I multiply by capital T. So actually, because of the rule that I have, the magnitude of my reconstruction filter is capital T. So T and T cancel. So in the case of impulses, actually you don't change the areas because of that. Okay? Just something to keep in mind. So this is your G, let's keep the hat on, G hat A of j omega. So what does it mean? What is the Fourier what is this in continuous time then? What is G hat A of t? What is that? So this is going to be cosine of which frequency? Pi by 3t frequency. Okay. So depending upon what t I selected, using the same sequence, depending upon what t I selected, I will actually generate different outputs. So let's say if my capital T was 1 by 30,000, then my G hat A of t is cosine of 10,000 pi t, or it's a 5 kilohertz cosine. If my t was 1 over 6,000, then this means that G hat A of t is going to be cosine of 2000 pi t, or 1 kilohertz. Okay. So using the same sequence, just by changing the time period t during my reconstruction, I can actually get completely different outputs. So it's very important for us that we make sure the time period that we use during reconstruction is what we intended. Okay. For example, if you recorded something at a sampling rate of 44.1 kilohertz, now you have just a bunch of numbers. And if you say now I'm going to reconstruct it, but instead of 44.1 kilohertz, you use, let's say, a time period that corresponds to 40 kilohertz, you are going to get completely different stuff from what you recorded. So what we understand so far is, if you take your continuous time signal, we know what the discrete time signal looks like because we know the Fourier transform of the discrete time signal. If you take your discrete time signal, convert it into continuous time, we know what it will look like because we know the frequency relationship. But the reason we do sampling is because we want to do processing. So the idea is, how do we use the information that we have gained so far for processing of continuous time signals using a DSP system? So in real world, what happens is that you are given this goal that here is an input signal GA of t. Someone will say, here is a song that I really care about in continuous time, and I want you to filter it according to some specifications to generate an output, let's call it YR of t for reconstruction, a reconstructed signal, and they specify some h of j omega that they want. So they want a filter to do certain things on continuous time signal. But you don't want to use a continuous time system to do this operation. So the way you do this operation in reality is you have GA of t, then you have an anti-aliasing filter depending upon the choice of your time period. So this is optional. And after that, you get this continuous to discrete block. To convert it into sequence, you get Gn. And then you pass it through a discrete time system. So you pass it through Hn or He to the j omega, however you specify it, to get Yn. And then you reconstruct it. with time period t to get yr of t. Okay. So this is what you want, and this is what we have. So how do we convert the continuous time specification that we really want into this discrete time specification? In order to do that, the first thing we need is we want to know what is h of j omega. And someone will have told it, this is what I want for that, so that's covered. That's not a big deal. Okay. The other question is, well, what should be the anti-aliasing filter? This depends upon the choice of capital T and the nature of your input signal. And you can determine that, again, using the information that you have available. You could say, well, I have a signal which has this bandwidth, so I must use big enough capital T, or my signal is not guaranteed to be band limited, so I'll have to pass it through first a low pass filter. That's not a big issue either. So the main issue then is, once you have selected your anti-aliasing filter, once you have selected the time period for sampling, the real question is, what should h of e to the j omega, or effectively discrete time system, be? Okay. What should you insert between the discrete time samples and your output system so that the discrete time system, this whole system that you have built, mimics what you want? Okay, that's the idea behind processing using DSP systems. So for the time being, we will sort of ignore the issue of anti-aliasing filter. What we are given is that you have GA of t, you sample it to get Gn, and you are now required to design h of e to the j omega to get back yr of t. And the idea is that this whole block from before the sampling up to the reconstruction, this whole block should mimic a continuous time LTI system with frequency response of h of j omega. Okay, so of course it's a continuous time system, because if you look at these dashed lines, the input is a continuous time signal, the output is a continuous time signal, so it's a continuous time system. What we want is that this whole dashed block acts not just as a continuous time system, but as a continuous time linear time invariant system whose impulse response or whose frequency response, either way, is doing what we want it to do. To be able to do that, we better know, we need to understand the relationship between h of e to the j omega, the filter that you have, and h of j omega which is the continuous time filter that you will end up getting. Now going forward, instead of calling this h of j omega, I'll be calling it h effective j omega, because this is effectively acting as a continuous time system, even though it really is not there. Right? We never explicitly put the continuous time system there. So to derive that relationship, and that's the way you do it in any sort of a block system, to derive this relationship, what we will do is we will take one step at a time. We will derive the relationships between the inputs and outputs of different blocks, and then we'll collect all of those relationships together to see what the output will look like. Okay. So let's look at the first. I'll start going from this backward. Okay. So we know, we just derived what is the relationship between the frequencies of the continuous time signal and the samples. We just derived that earlier, right? If you start with samples, the relationship of yr j omega, the output, is simply the reconstruction filter hr j omega times the Fourier transform of y scaled by a multiple which is given by your time period t. So the notation I'm using is the Fourier transform of this is y of e to the j omega. The Fourier transform of this is yr of j omega. We already know the Fourier transform here. The Fourier transform of this is g of e to the j omega. And the Fourier transform of this is ga of a to the j omega. Okay. So we are just right now focusing on the last block. We are moving backward. We already know, we just derived it, this relationship. Right? And this is always true. It doesn't matter if your t was certain range or whatever. Right? Now let's look at the relationship between the output of the discrete time LTI system and the input of the discrete time LTI system. So what is that relationship? Well, the output of a discrete time LTI system is simply the input Fourier transform multiplied by the frequency response. So that's x of e to the j omega, h of e to the j omega. This is always true also. Okay. So we have now covered this block from here to here. This is block, we just did 1. We have covered from here to here, this is block 2. Let's now look at what is the relationship of this block 3. Okay. So that is, what is the relationship between g, sorry, it should not be x, it should be g. Okay. What is the relationship between g and Fourier transform and the input continuous time Fourier transform? Again, we just went through it earlier. That is g e of j omega is 1 over t summation k from minus infinity to infinity ga of j omega minus 2 pi k over capital T. And again, this is always true also. So regardless of what happens, whether you have aliasing or not, these three relationships are true. What we want is a relationship between the input continuous time signal and the output continuous time signal, because that is what will describe whether we have an LTI system or not. So let's just start plugging in all of these things. Right? So plug 3 into 2. What do we get? Y of e to the j omega equals 1 over t summation k from minus infinity to infinity GA of J omega minus 2 pi K over T times H of e to the j omega. Now let's call this 4, and now plug 4 into 1. Okay. So 1 requires y of e to the j little omega with little omega replaced by capital omega t. So we just plug 4 into 1 and replace little, wherever we see little omega, replace it by capital omega t. So if I do that, I get yr of j omega equals to hr j omega times 1 over t summation k from minus infinity to infinity ga of j capital omega t minus 2 pi k over t, and h. So we have to now, because h is also a function of little omega, we have to replace that with capital omega t also. Okay. So we still don't see GA of j omega. We are trying to get to that. But let's just simplify it a little bit further. YR j omega. Since this does not depend upon k, I'll just take it out. So I get h of e to the j omega, which is just a scaled version of the Fourier transform of your discrete time system. Okay, this is just h of e to the j omega with omega replaced by capital omega t. So I get this times hr j omega times 1 over t summation k from minus infinity to infinity ga of j. I'm going to just write it into two terms, 2 pi omega minus 2 pi k over t. Okay. Now this expression, as up to this point, you will note that I have not made any assumptions on anything. What is the reconstruction filter? Whether we had aliasing or not. So this is always true. And if you are interested in getting something, finding out what the output will look like, you can do this expression and find out what will be the effect of having a system in your, having a discrete time system in your block diagram. But in an ideal setting, what do we assume? In ideal setting, the first thing we assume is, so ideally, the first thing we assume is you're sampling at a high enough rate that you satisfy the Nyquist criterion. Okay? So ideally, T in continuous to discrete converter is such that the Nyquist criterion is satisfied. Okay? And what is the other ideal assumption that we make? That the reconstruction filter corresponds to sinc interpolation. It's a perfect low-pass filter. So HR j omega is an ideal reconstruction filter which means that it is equal to capital T for omega less than or equal to pi by t and 0 otherwise. So now let's analyze the boxed equation under these assumptions. Okay. If you analyze the boxed equation under these assumptions, the first thing we know is that for k equal to 0, GA of j omega lies between minus pi by t and pi by t. That's because that is the Nyquist criterion, so it has to satisfy that. And for k not equal to 0, GA of j omega minus 2 pi k over t, those are the other copies that are now located at 2 pi over k minus 2 pi over k and so forth. Those copies are outside the minus pi by t to pi by t range. So for k not equal to t, these lies outside capital omega belonging to minus pi by t to pi by t. So what does, then if I just focus on this inner block of this equation, what does that say? That all I am left with is the main copy, which is at 0, multiplied by hrj omega, because everything else gets zeroed out. It's the same argument that I'm making when we did the reconstruction filter explanation or sinc interpolation. Yeah. So because of that, under these assumptions, what we get is that hrj omega 1 over t summation k from minus infinity to infinity ga of j omega minus 2 pi k over t is nothing but equal to hrj omega 1 over t ga of j omega. Okay. It's the same argument that we made during the reconstruction. Okay. So I am now going to, under these assumptions of 1 and 2, I'm going to plug this expression, this star expression, into the red boxed thing. So what I get is yr of j omega is equal to h of e to the j capital omega t times hr j omega, and I have not replaced the value of hr j omega, but we'll do that soon, ga j omega. Okay. So what is hr j omega? The compact form of that is, of course, t times indicator function from minus pi by t to pi by t capital omega, which means it's 0 outside minus pi by t to pi by t. So when I do that, the t cancels and I get h of e to the j omega t indicator minus pi by t to pi by t capital omega ga of j omega. Okay. So now we have been able to write, if you want to show that something is an LTI system in frequency domain, you better be able to write the output frequencies as equal to input frequencies multiplied by some sort of a Fourier transform. And we have been able to do that. We have shown, we were interested in this block diagram, H effective j omega, output is yr, and input is ga of t. And we have shown that the output frequencies yr j omega are multiples of input frequencies ga j omega times this expression of capital omega. So this is as if this whole thing, which is circled, is acting as a continuous time filter. Okay. So what it turns out is that your effective filter is nothing but a scaled version of your discrete time filter up to the minus pi by t to pi by t range. Okay. This is what your effective filter will look like, but only from minus pi by t to pi by t. Under the assumption that A, you had no aliasing, i.e. you satisfied the Nyquist criterion, and B, you had an ideal reconstruction filter. What does it pictorially mean is that, let's say my discrete time filter was such that, so say Hn was such that h of e to the j omega, let's say it's a low pass filter, okay? So it is 1 for little omega less than or equal to little omega c, and 0 otherwise in omega belonging to minus pi to pi. Of course, it has to periodically repeat itself. If this was the case, what it is saying is, if you implement this discrete time system, this discrete time filter in your block diagram, effectively what is happening is you are actually doing a continuous time filtering, where the continuous time filter is given by just h of e to the j capital omega t times 1 minus pi by t to pi by t capital omega. So what this means is, what is this relationship? That is the scaling of the frequency axis, right? So your h of e to the j omega looks like this. It's a low pass filter. So it has a cutoff omega c minus omega c, height 1. What is this saying? That you replace little omega by capital omega t, which means if you want to derive your equivalent filter, you scale this whole frequency axis by dividing it by t. Okay? So this is your h of e to the j omega. Your h of e to the j capital omega t will then simply look like a scaling of the axis. This will become omega c over t minus omega c over t minus pi by t, and then things will repeat. And then because of this relationship, what it is saying is you only focus on whatever you have between minus pi by t and pi by t. So your effective filter is simply, it looks like this, with a cutoff of omega c by 2 minus omega c by 2 and height of 1. Which means that if you had a low pass filter in discrete time, that will effectively be, if you focus on this shape, this is a low pass filter in continuous time, right? So what that means is a low pass filter in discrete time acts as a low pass filter in continuous time, but the cutoff frequencies are scaled by 1 over t. So if you have a low pass filter with a cutoff of pi by 2 in discrete time, in continuous time that will have a cutoff of pi divided by 2t. Okay? And similarly, you can derive other effective filters that you get if you do this scaling relationship. We'll try to remind ourselves of some of these things on Monday.